Welcome to part 2 of Principles of Magnetism and Electricity. If you have not watched part 1, I would suggest that you find part 1 on the PLC Professor YouTube channel and watch it first. This is not a separate lecture, it is the second part of a whole lecture that was too long really to put as one video on YouTube. Force and motion. Some years ago I coined a phrase, you can make a motion but you have to force the flow. So this had more to do with marketing for wind energy and solar energy. It really had nothing to do with basic electricity magnetism. However, if you think back into part 1, you could take a magnet and move the magnetic field through a conductor, and the magnetic field produced by the electrons in the magnet put the electrons in the conductor in motion, but then they immediately stopped. If you want flow, you have to force it. You have to have a continual pressure, and you have to have some sort of force to keep something flowing. So you can make a motion, but you have to force the flow. And so this is the topic in this second half, is actually talking about force and motion. One of the pleasures of lecturing is finding real-world examples or examples from everyday life, or finding illustrations that people can identify with to explain electricity and magnetism. So you're probably wondering, what does this photograph of a old western town and a water tower have to do with force and motion? Well, you have two water tanks there. Maybe you didn't notice the second one, but halfway down the tower or so there's another tank. So when you look at these two tanks, let's say they're both full of water. If you were going, and let's say you had separate pipes coming down from each tank with a valve and a shower head, and you were going to stand underneath there and take a shower, which tank do you think would provide the most water pressure? Now, you would probably say, well, the highest one. Well, put in scientific terms, it would be the one that has the greatest potential. So the upper tower has a higher potential than the lower tower. Now, potential energy. So it took more energy to get the water up to the higher tank, so you get more energy through the water when you release the water to come back down. So if you look and relate this to voltage, the upper tower has a higher electrical charge than the lower tower, but it took more energy to force more electrons away from their atoms to create the greater charge. So the higher tower represents a higher voltage, but it took more work. So you don't get anything for free. There's an old saying, there's no such thing as a free lunch. And the laws of thermodynamics, one of them says, you can't win, you can't even break even. So there's laws of efficiency. So anyone who proposes a free energy system is deluding themselves. It always takes more energy to produce the form of energy that you want than what you're going to get out of it. So if you want to put it in kilowatts, it's going to take more watts. If you want to take something like water power and generate electricity, the electricity, usable electricity that you're going to get will be less than the water energy that you use coming down through gravity. However, that doesn't mean that the system's bad. That's just a fact of life, that anytime you convert energy from one form to another, you lose something. But these systems still work very good. Another illustration that could be made from these two tanks would be stretching a rubber band. If you were to anchor a very large, long rubber band at the bottom of that tower, and we'll say the rubber band was 4 foot long, meaning it's 8 foot of rubber in a loop, okay? And so you anchor at the bottom of the tower and you stretch it up to the top of the middle tank. It's going to take a certain amount of energy to do that. But to stretch the rubber band all the way up to the top of the higher tank is going to take a lot more force and a lot more energy. Consequently, if you stretch the rubber band to the top of the middle tank, the lower one, when you release it, you get a little snap. And if you stretch it all the way up to the top of the higher tank and release it, you're going to get a big snap. So if you just look at potential energy in terms of stretching a rubber band, the further you stretch it, the more energy it's going to take to stretch it, but the more energy you're going to get when you release it. Just like shooting a rubber band, you hook it over one of your fingers, pull it back. The further you pull it back, the further it's going to travel when you release it. Well, as long as we're looking at water towers, why not just continue on with that example? Actually, I created these graphics first, then I found the picture of the water tower. In other words, I was looking for a real water tower, and I happened to see the one in that old western town and thought that was more interesting. So here is your public utility for water. Somewhere there's a pumping station, whether it's pumping it out of a well in the ground, out of an aquifer. And there's two ways to spell aquifer. I picked one, and I'm not going to change it. I think the other spelling is more dominant, but I already put this one in here. So just in case you notice that, don't be distracted by that. Aquifer, that just means groundwater, or actually it's a pool of water in the ground. It could be an underground river as well. In Michigan, in western Michigan, where I spent quite a bit of my life, they actually pump the water out of Lake Michigan. And there's a pumping station halfway between Lake Michigan and Grand Rapids, which is about a 35-40 mile distance. So water is pumped out of some large endless reservoir of water, underground or a lake, and it's pumped into a tank. So this is the charging system. So we're going to charge our system with a pump, an electrical pump that will have some controls on it, and we want to keep this tank as full as possible. The tank itself is storage. If there's no water in that tank, there is no force of gravity on the water that's felt down through the pipe. If we open a valve in the house, we have flows. So water flows out of storage through the residence, through the drain into the soil. It could be a septic tank, or it could actually go to a waste treatment facility. We'll just say it goes into the soil in a septic tank. And if you know anything about septic tanks, the solids settle to the bottom, and then the water leaches out into the soil. And as it travels down through the soil, it's filtered and cleaned and purified, and then it goes back into the aquifer, or somehow it gets back to the source. How much flow that you have, if you think about this, you've got, let's say that's 10,000 gallons up there. If you opened the valve, why wouldn't all 10,000 gallons come down instantly? Well, you realize that's absurd, but we're just making a point here. Why wouldn't all of that water come down in an instant? That's because flow is limited by resistance. So pushing back against the force is the size of the pipes. The valve changes in direction as the water flows down and goes back to the soil. Now I realize that inside your residence you have bathtubs, showers, sinks, ice makers in your refrigerator. All of these are points of resistance that are controlled to control the flow. But even if you opened up that pipe right where it enters the house wide open, the flow would still be limited by the resistance of the size of that pipe, the friction on the inside of the pipe. Looking at our system in very light mathematical terms of ratio and proportion, and I want to further elaborate that pipe that comes down from a storage tank to your house, another way for you to look at how the size of that pipe, in other words the inside diameter of the pipe, affects the flow, is if you compare it to a straw. I'm sure at some point in your life you have had something thick to drink out of a glass, out of a cup, or some vessel, and you put a straw in there, and the straw was kind of skinny, or a very small inside diameter, and you had to suck really hard to get what you wanted up out of that glass or out of that cup. If you had a larger straw, you still had to apply a fair amount of force, in other words suction, but you got less resistance from the actual straw. You still have some resistance from the weight of what you're pulling up through the straw, but the larger the straw, the less resistance you have from the straw itself. So I think this is a very easy to understand illustration. So if we put force, flow, and resistance in another form, we would say that flow is equal to force divided by resistance. So let's just stop and look at this a minute. I think that probably most people that are watching this video understand basic ratio and proportion, or fractions. So here we have force over resistance. If the force increases, the flow increases. If the resistance increases, then the flow decreases. So in mathematical language, we would say that force and flow are directly proportional. More force, more flow. But then we would say that flow and resistance are inversely proportional. The more resistance, the less the flow. So force and resistance are inversely proportional to flow. That's why they're placed with force above the line and resistance below the line. So I think this is very easy to understand. And when we actually, if we were to get to so far as to quantify electricity, this would read current flow equals voltage force divided by electrical resistance. So the greater the voltage, the greater the flow of electrons. The greater the resistance, the lower the flow of electrons. And if you want to relate that back to the earlier parts of this presentation, remember that copper has one valence electron, one free electron, and copper is a very good conductor. However, silver is better than copper, and gold is even better yet. And that is because the heavier materials, although they still only have one electron in the outer orbit, that outer orbit is further away from the nucleus than it was in the copper atom, which means that in gold, that outside single lone solo electron in the outer orbit is more loosely attached to the nucleus than they are in copper. So the electrons are more easily displaced out of a gold atom than out of a silver, and silver more easily than out of copper. Therefore, you can say that gold has less resistance to electron flow than silver. Silver has less resistance to electron flow than copper. So for right now, we'll just keep it in those simple terms. Now, how would you compare that to the pipes? A we'll say a copper electrical conductor would be analogous to a 1-inch inside diameter pipe, silver a 2-inch inside diameter pipe, and gold to a 5-inch inside diameter pipe. So think of the mathematics involved here in these very simple terms: directly proportional, inversely proportional. So let's quantify our public utility freshwater system here. If we want to quantify the amount of force, we're going to do that in terms of head, and we'll do it in feet. So head pressure is the height of the top of the water column above the point where you're going to use it. And that includes the water in the tank too. Now, if this tank were twice as large in diameter, but the water level still was no higher than what you see here, the head pressure would remain the same. Even though you're thinking, well, there's more water up there, this is done with a vertical column. So if you take and travel straight up the pipe, and when you get to the bottom of the tank, you keep going straight up to the water level, that's what you're measuring. You're measuring the amount of weight straight down through that pipe, and that's measured in head. You can also relate it to pounds per square inch. And what we're talking about is gravity, right? Atmospheric pressure, gravity pressure. If we take that same tank, and in a case where there's high water usage in your neighborhood and the pumping station can't keep up with the usage, and that's not uncommon. However, the pumping station takes into account that tank can get almost down to empty. As long as it can keep it from going empty, everybody has some water. But the water pressure does reduce because the head, or the height of the water, the top of the water column, is now lower, so you have less pressure. This would be very easy to compare to a battery. When a battery is fully charged, that's like a full storage tank. As the battery discharges, like when you're starting your car on a cold winter morning and it's just cranking away, and pretty soon you start to hear it a little slower, that would be the tank over on the right. What you had stored up in your storage battery is now being depleted. Now, although that battery can recover chemically, you're still going to need to get the car started to run electrons back in the negative side of the terminal to build the charge back up. This is a very good comparison of the voltage dropping when there's a high demand. So almost in any household, you have at least one device that when you turn it on, the lights dim. In other words, you might be sitting there and then all of a sudden you see the lights kind of flicker. That could be because an air compressor kicked on in the garage, or the sump pump kicked on down the basement. Usually most appliances don't have that much instantaneous drain, but it's all comparable to what we're talking about right here. Here we have two different residential public utility freshwater systems, and considering what we've talked about so far, I think the first thing you would notice is the one on the right has a higher tank than the one on the left. Therefore, the one on the right will provide a higher water pressure than the one on the left. Now, in my place down in the Dominican Republic, all homes down there, if they have what you would call running water, it's from a tank on the roof. So we have an on-again, off-again public water utility that sends water at different times of the day up into our neighborhood into a pipe. And we have a reservoir, a cistern, underground. And so that public water flows into that cistern. And when we have public power, because the power goes off every day, we have a electrically powered pump that pumps water from the cistern underground to a tank up on the roof of the house. And we have a float switch inside of that tank that turns the pump on if the water level drops. So usually what happens, the power goes out every day and you keep using the water. The instant the power comes back on, the pump kicks on, it pumps water up there. The point I was going to make was that my bedrooms and office are on the second story. So the water tank is about 4 feet over my head when I'm taking a shower, and the water travels a very circuitous route to get to the shower head. It actually goes down and then back up to the shower head through the hot water heater. So the water just basically dribbles out. But downstairs on the first floor, they get reasonable water pressure. I'm not complaining, but if you wanted to, you could say that this represents a low voltage system and a high voltage system. So the one on the left would be, say, 24 volts DC, and the one on the right would be 48 volts DC. It takes more energy to charge the higher system, but you get more energy out of it. You have more force through relatively the same amount of resistance. Now you could argue that there's more pipe going down the downcomer down to the house on the right than there is on the left. So there's a little bit more resistance over on the right, but believe me, you're going to get a lot more pressure from the system on the right than the one on the left. Okay, we've upgraded our public utility for fresh water to include your neighbors, and you're on a little dead-end street. Now we know there's going to be more than 4 residences on a water tower, but this is good for our illustration. Looking at this picture, if you were going to define the difference between residence A, B, C, and D, since A, B, C, and D as far as a house is concerned is identical, its sewer pipe or waste lines are identical. The only difference between the 4 is the downcomer, or the plumbing coming from the water tower down to the houses. Now there's really only one large pipe coming down from the water tower, but to keep the diagram simple, I did something a little bit different, but the illustration is still good. House A and B are being fed directly from a pipe, but house A has a longer pipe with 2 elbows in it. Houses C and D, not only do they have an elbow or 2, but both homes have to draw their water through the same pipe. So the resistance of that initial pipe is affecting the flow to both residence C and D. So that having been said, which home here, which residence, A, B, C, or D, would have the greatest flow of water? And remember, all 4 of the homes have the exact same pressure. When there's no water flowing through the pipes, and you were to measure PSI or pressure at the entrance to each home, the pressures would all be equal. So you're thinking, well, why would the flow be different? Well, we'll see. Which residence will have the highest available flow? B. B has the least resistance. Now remember, when there was no flow, the weight of the water in the vertical column was the same because it's based on the height from the point of entry up to the water level in the reservoir, the tank, the storage unit. But once the water starts to flow, the pressure, some of it is dissipated in friction against the sides of the pipe. Which residence would have the lowest available flow with this given system? Well, A would be a little less than B, simply because it's got a longer distance to travel through the pipe, and it's got 2 direction changes, and these direction changes produce heat from friction as the water travels with more pressure against the outside of the turn. Now that's small, but it's still there. residents C and D, they share one common pipe coming out of the reservoir. So that means C and D are definitely going to be lower than A and B. Even though C is the same as A concerning pipe and distance, because it has to share the flow from one common downcomer with D, that puts C less than A. So which one would have the lowest available flow? Well, D. Not only does D have to share a downcomer, but it has a greater length of pipe to travel than A, and it has two elbows in it, just like A does, but it's a longer distance, plus it has to share the downcomer. Okay, what determines how much water flows through one of these residences? Now, this is not a trick question, but you've already been given the answer. Flow equals force divided by resistance. So when we compare these four residences, we compared the resistance. The force is equal, but the resistance is greater in D. C is greater than A and B, A is greater than B, and B is the least. B has the least resistance to flow for the same force, so it's going to have more flow. Okay, so how could we control the force? All of these families are paying the same rate to the public utility for water usage. However, the folks in House D happened to visit the folks in House B, and they noticed when they went in to wash their hands before dinner that they had a lot more water flowing, a lot more water pressure and more flow out of their faucet. And they thought, well, maybe they've got better faucets or better plumbing. And a couple days later, the husband's out in the backyard at House D, and he's got a hose hooked up to a spigot, and he's spraying something, and his neighbor's got the exact same length of hose. They happened to be together when they bought them at the local hardware store, and he can't get his water to shoot out as far as the other guys. So he starts checking, and pretty soon he realizes he does not have as much water pressure as the family in A and B. So since they're all paying the same dollar, the power company had to do something to equalize the pressure. And so they came up with this device. It's called a pressure regulator. Now, I realize that this is not electrical, but it is demonstrating the balance of force to control the force. So you notice on our regulator here, there's two flange mounts. One on the right that has an arrow coming in from the tower, and one on the left that's going out to the residence. So this could be mounted horizontal, and the pipe comes down from the tower, takes a 90, goes in, comes out the residence side and goes down to your house. Or it could be mounted vertical. It doesn't matter, because this device is not dependent upon gravity. It's dependent upon pressure. And there's two pressures at work here. One of them is the spring, which you can see kind of a cutaway view there, and maybe you didn't recognize that right away if you're not used to looking at this kind of a diagram. But in the upper portion of this regulator, you see the cutaway view of a coil spring. At the top of that coil spring, you see a threaded bolt with a lock nut, so you can take and screw that bolt in, and that compresses the spring. Now, what you may not see quite as easily is that spring pressure is pushing down because it's pushing against the outside of the casing. It's pushing straight down. If you follow the rod down, you'll see a clapper. It's a valve where you see the little arrow representing the water that comes in from the tower, goes down and then comes back up on the other side of that mechanism to go out the residence. So the water has to get through that valve right there, and the spring is forcing the valve open. So this diagram is drawn with the water pressure from the tower. Um, well, it's drawn with the valve closed. So let's continue. Okay, this is the pinch right here. So if you were going to control water flow through a garden hose, what do? You pinch it, right? You either fold it so it's completely pinched off, and then you walk over to where you want to continue, then you release it and you get your flow grin. Or if you're trying to keep the water from not coming out so hard and washing away, we'll say, the soil out of the pot that you want to add water to for your outdoor flowers, you kind of semi-pinch the hose to reduce the flow. That's basically what this regulator does. But what the regulator does is it pits the water pressure from the residence. In other words, the water comes down from the tower, flows through this valve, it fills up the pipe between the regulator and your house, and as it fills up, the water pressure backs up from the house into this regulator, and it pushes against that spring to close the valve. So when you open a valve in your house, the water starts to flow out of the residence side of this regulator, the pressure drops, the spring takes over and forces open the valve, the tower sends more water in, and so it's always a balance between the backed up water pressure from your house and the residence side of this up against the spring and the spring tension. So the adjustment of the spring determines how much water pressure you're going to get. It's a regulator, it regulates pressure. So there's the spring, and the spring is pushing down to open the valve. The water pressure from the house is pushing back to close it. And when they're equal, then the valve is going to be closed. So this is adjusted, the bolt on the top of this regulator is adjusted until the water gauge at your home entrance equals roughly 45-50 pounds psi. That's how you adjust these regulators. So if we go back to our residential system and we install one of these regulators in all four downcomers and we adjust them each to 50 psi, then all four residences will always have 50 psi, unless of course the tank up above goes empty. Typically these regulators are sized or adjusted so when the tank is almost empty, you still have enough force on top of the regulator to be greater than the force coming back from the house. So in other words, if the force from the tank got lower than 50 psi, then all the regulators would just be wide open. And actually that's what happens if you let that reservoir up in the water tower go empty. The regulators are wide open because there isn't enough force from the houses coming back because you're draining away the water. It's time now to make the transition from gravity and water flow to voltage and current and electrical resistance. Electrical current would be analogous to flow. So gravity gave us water pressure, which gave us flow, opposed by the resistance. Electrical current is the motion or the movement of electrons through a conductor from atom to atom. One thing I did not emphasize before, and it's not that important, is that if you wanted to, you could look at the free electrons, one per copper atom. You could look at those kind of as a pipe full of ping pong balls, all tight, pushing up against each other. If you have a pipe 1 mile long and its inside diameter is exactly the size of a ping pong ball, just a hair larger to allow the ping pong balls to move easily, if you force another ping pong ball into one end of the pipe, one's going to pop out of the other end, but not the one you forced in, the one that's closest to the other end, because remember, electrons are negative and they repel each other. So if I place one extra electron in one end of the wire, that bumps all of the free electrons over one atom all the way down through the conductor, and one electron pops out the other end. Now remember, in order to get current to flow, electrical current, electron flow, I need to put a negative charge on one end and a positive charge on the other. So remember, the negative charge is an excess of electrons, and the positive charge is a deficiency. So if I put that charge across the conductor, one of the excess electrons is forced into one end of the wire, and the positive charge on the other end pulls out one electron. So the number of electrons in the copper wire stays consistent as you're forcing electron flow through the wire. So flow is electrical current. The force that we use for water flow is gravity, or pounds per square inch water column, head, however you want to describe it. The force for electrical current is voltage. It's measured in volts, and it's just referred to in general as voltage, but it's really EMF, electromotive force. It's the electrical force that motivates the electrons to move. And the greater the voltage, in other words, the greater the potential force across that conductor, negative on one end, positive on the other, the more excess electrons and the more deficiency of electrons you have, the stronger the pull to pull those electrons traveling along the copper wire. And of course, resistance is resistance. In a water pipe, the resistance was the friction on the sides of the pipe. And the reason a smaller diameter pipe has more resistance than a larger is that when you apply force to push water through the pipe, that force is also against the sides of the pipe. So you're actually pressing the water that flows along the sides of the pipe tighter and tighter against the side of the pipe. That increases friction. So the greater the force that you have, the more it pushes against the side of the pipe, and basically it dissipates in the form of heat. You wouldn't believe that, but water flowing through a pipe does heat up the pipe, but not to the touch. It's just a fraction of a degree. Electrical current, the resistance to current flow from voltage, is measured in ohms, and we're not going to get into the math, but as I explained that copper is a good conductor, silver is better, and gold is even better yet. Therefore, there are conductors that the electrons are more easily moved than other conductors. Some materials you can't move the electrons at all under normal voltage pressure. They are insulators. However, if you apply a high enough charge, a strong enough force, just like if you have a high enough water force, it will burst open and destroy the system, but there will be flow. So an electrical system, and a good example would be in a thunderstorm, if a bolt of lightning hits the power lines and sends a surge into your house, the plastic and rubber insulation on all of the conductors running through your home have a rating usually of 600 volts. If that voltage is exceeded, and they measure the ability of a material to insulate electrically, they call it a dielectric strength. So if you exceed that dielectric strength, in other words, you have 10,000 volts that comes in, and you have insulation that's good for 600 volts, you're going to get electrical conduction through that insulation. But it's going to destroy the insulation because it is literally ripping electrons off of the atoms with such a violent force that it's going to destroy the material. So there are other materials that are called semiconductors, and they allow electrical conduction but not as freely as copper, silver, or gold. So there are a variety of ways to control electrical flow. You can control it with a field. If a magnetic field, which is made up of the magnetic fields of many electrons, if that magnetic field can induce a current to go one way, another magnetic field can inhibit it from going that direction and control it. So you can control electron flow with a magnetic field that's trying to push it in the opposite direction. So the end result, or the flow, is going to be a balance between the two forces. One's pushing it one way and one's pushing it the other. The one that's greatest is going to dominate, and the difference will be reflected in the actual current flow. So as you increase and decrease one of those forces, the current flow increases and decreases. Let's step up to another level of analysis of what's going on here. In electrical circuits, in order to have flow, in other words, in an electrical circuit where you want to have flow, you want a complete circuit. And that complete circuit is the path in which has been designed to carry the electrical flow. In the case of our water system, the water pumps up to the tank, the reservoir, and then gravity carries it down through the house into the waste system, into the soil, into the aquifer, and it's reavailable to pump back up again. Now, just as the water molecules that come out of your waistline don't necessarily end up going back through the pump to your tank, they are available to systems throughout the world. Electrons are available basically through the ground. And if you've ever heard that term, well, it wasn't grounded, or it needs a ground connection. We have a phrase that we've said for years: ground is ground the world around. A lot of electrical systems actually use the ground as one part of the electrical path to complete the circuit. So if you grab one side of the 115 volt AC line in one of your outlets, and your feet are standing on a wet spot on the ground, you might get electrocuted because electricity will flow through the ground. Remember, the ground's made up of many elements, some of which are conductors. Now, not all ground is a good conductor. Sand, dry sand especially, is very poor. But anyway, you see the idea of a complete circuit. And this is the complete circuit that we've been working with so far. And there's something called circuit theory. The theory of accomplishing work by routing electrons, fluids, or any other matter through loops: water, natural gas, petroleum, electrical, hydraulic, or pneumatic. Now, normally in a pneumatic circuit, it resembles more the residential water supply than the rest of them do, because with a pneumatic system, you pump air out of the atmosphere into a storage tank and until it gets up to a certain pressure, and then you use that air pressure to and you control it with pneumatic valves to get cylinders to extend and retract. Normally, once you've used the air to push a cylinder forward, it exhausts out into the atmosphere, which would be like the aquifer, only for air. So circuit theory is the study of all these different kinds of complete circuits. So how do we control the flow of water through the residence? Well, we start with a float switch in the tank. And down the Dominican Republic, my float switch that I put in my tank is actually just a bulb on the end of a conductor that floats freely on the surface of the water, and it works on attitude and gravity. So as the water lowers in the tank, the float starts to angle down, and when it gets far enough down, then gravity carries the weight inside of the switch bulb to close the switch. And then of course it turns on the pump, the water pumps back up, it starts floating back up until it's above level and tips the other direction, the other attitude in the opposite direction, and the weight slips the other way and opens the switch. So here we have a float switch, and there are other ways you could do this. You could do this with a float valve, where the float actually closes a valve and fights the pressure from the pump. Now that's not a good idea because you don't want the pump running. So we use a float switch. Then we have a pressure regulator that regulates the amount of pressure that's actually felt at the residence. That gives you nice consistent use of the water. And then of course you control water flow with valves. Or you have a valve in your refrigerator that controls water flowing into the little ice cube cavities. The water in your hot water heater, that's strictly water pressure. So, and that's good because you want the water pressure from the tower to be felt all the way through the hot water system to your hot water valves on your sinks and shower. That way you've got water pressure for the hot water. So it's the cold water pushing on the hot water in the hot water tank that pushes out the hot water for you to use. This is an electrical circuit, and we're going to draw some direct comparisons between the public utility freshwater system and this electrical system. Instead of a water pump pumping water from the aquifer up into the storage system, we have an AC power source from the public grid. In other words, the pole outside of your house comes in through your service entrance, goes through your service box downstairs, you call it the breaker box, and in there are a number of circuit interrupting devices that if you were to draw too much current, they would pop open and not allow your house to be burned down. We also have a switch to complete this circuit. So we had a float switch in the tank that turned off the pump if it was full. So this switch, we basically turn on the whole circuit with this. So it is slightly different. But we do need a way to turn this entire circuit on and off. Then we have a battery to store the electrical energy. So the electron flow in this case actually is going from the AC power source down through the wire and up into the bottom of this cell, and then coming out the top are electrons going back to the AC power source. So we're charging up the negative side of the battery with electrons, and we're removing electrons from the positive side of the battery. So we're adding electrons to the negative side and removing them from the positive side. They're not the same electrons. So what we're doing is we're creating a charge, an electrostatic charge between the outer shell of this cell, which is negative, and the inner pole, that cathode or graphite rod in the middle, is now missing electrons, so it's positive. And there's another little symbol up there by the switch that looks like an arrow. That's actually a diode or a rectifier, because we have an AC source, meaning the current is going back and forth. It's switching direction 120 times a second, which gives you 60 hertz, 60 cycles. A complete cycle is current goes one way, then goes the other. That's one cycle. So you get 60 of those a second. But we only want current to flow one way through that battery, and that's to charge it. That's why we have that diode in there. Now we also have a switch to complete the circuit from the AC power source to the LED, or from the battery to the LED. We have a light emitting diode, which is, we're not going to get into the discussion of how the light emitting diode works, but it basically is a conductor, but it has some semiconductor material in there that gives off light instead of heat. And then of course copper wire is connecting everything. So remember, our water system had a charging system and it had storage. So we would use the charging system to charge the battery or to directly power the light. And basically the end result here, or the desired result, is flow, electron flow. So flow is determined by how much force and how much resistance that we have. In the case of electrical circuit, we're going to call it voltage, electrical current, and resistance. So the more voltage, the more electrical current for the same resistance. Now if the switches are open, that is an infinite amount of resistance. There's going to be absolutely zero current flow, electron flow, through an open switch, because electrons cannot jump across the air. Now that's not totally true, and I will show you in a minute what I mean by that. But for the voltage that's supplied by this cell, when fully charged, gives you about 1.5 volts, so 1.5 volts. At 1.5 volts, that's not enough pressure to make electrons jump across the air gap of an open switch. Now I said that the electrons can't jump across the air in an open switch, but I said that wasn't always true, but it was true in a circuit where you're limited to 1.5 volt. Let's take a couple other situations here. The first one that everyone has experienced, and that is where you have static electricity build up on your body. Now I'm showing your finger very close to the doorknob, and the red cloud there is kind of the electrostatic field between the electrons, the excess of electrons in the doorknob, and the deficiency of electrons in your hand. It could be the other way around, just depends on how you generate the static electricity. But keep in mind, when you were 10 feet from the door, there was an electrostatic field that extended from your body out to everything around you. However, the field is going to be strongest between you and a source of the opposite charge. Remember I said ground is ground the world around. So this doorknob really isn't ground, it's probably neutral. But neutral is still either less positive or less negative than what your body is. As you draw near to that doorknob, that electrostatic field intensifies between the positive and negative charges. And the closer you get to the doorknob, the stronger the field becomes. The voltage actually increases. So you've got two things working here. The voltage is increasing, the field strength is increasing, and there's less and less air molecules between your skin and the doorknob. And when you get close enough, you get an arc, and that arc discharges the difference in potential between your body and that doorknob. So this is an example where electrons do jump across air. Now, what I do, if I know I'm going to get shocked, I walk up and I slap the doorknob. So the pain of hitting the doorknob with my hand is greater than the sensation of the arc. I don't like getting shocked. As an electrical engineer, I've gotten some pretty hard hits over the years. None in the last 30 years probably, because when you're young you do some real stupid things. Got to tell you a story real quick. When I was in the Marine Corps, my primary MOS was microwave radio relay technician, which means I was a grunt, a ground pounder, but when I wasn't fighting I was repairing microwave equipment with microwave wave guides, directional antennas, everything. But when I was in class learning about radios, we had these AM radios. They're really for military use, not for civilian use, but you could tune in local stations. So I'm sitting there and I'm supposed to be doing one thing, but what I did is I took one of my meter leads, I stuck it in the coax output for the antenna, and then stuck the other end behind my ear and under the headset. So my body was basically an antenna to improve the reception. I'm sitting there jamming out, listening to tunes, right? So here comes the instructor. Remember, I'm a private, and here comes this gunnery sergeant, big old nasty, hairy, gnarly gunnery sergeant who's teaching the class. So I didn't want to look like I was goofing off, so I quick grabbed the other end of that lead out of the coax connector for the antenna, and I went over, and without thinking I put it on the B plus cap on one of the power amplifiers that had like 200 volts on it, and I got 200 volts through my ear. So that was a hard shock, but it was my own stupidity. It wasn't static electricity either. It was a continuous current. Another example would be opening a switch that has current flowing through it, and as you open the switch, you're creating an air gap. The electrons are still trying to flow. There's still voltage there. If the voltage is high enough, you're going to get an arc. So watch this as the public power utility guys are opening a switch to do work on a substation. I did not film this. I grabbed this off the web. 138,000 volts. What you witnessed there was an arc. Now you're probably wondering why they called it an arc. Why wouldn't the electrons just flow in a straight line across the airspace? Why does it actually form an arc? Very simple. Think about it. As you rip electrons off of the air molecules, you produce heat. So you produce an updraft that carries the ionized air upwards. Cool air rushes in underneath to take its place, and then the arc just continues to rise, and that increases the distance that the electrons have to flow through the air, and pretty soon the distance is too great for the voltage. In this case it was 138,000 volts. Then the arc is interrupted. Okay, here's our circuit. We have a switch closed and a switch open. So basically we have the circuit completed for charging the battery or charging up the storage. So remember, this is an AC source, so in one polarity electrons come out of the AC source, come in the bottom of the cell, replacing the electrons that have been dissipated in the outer shell of this cell. Electrons come out of the center rod, the graphite rod, the cathode, and go to the AC supply. When that half cycle is completed, and then we see the other direction, notice the negatives on the top, now positive on the bottom of the AC supply, that diode will not allow current to flow in that direction. If it did, then electrons coming out of the AC supply would go up and down in the positive side of the battery, thereby discharging the battery. So we want those positive charges on that center rod, that graphite rod. If you ran electrons in there, that would complete them and you wouldn't have any voltage to work with. So if you're going to charge up a battery, you need direct current, not alternating current. And you can get direct current from alternating current by putting in a rectifier, a diode, which will obstruct one half cycle and only allow current to flow in one direction. So the battery is charged up. Now we open the charging circuit, and now here you go with your charged up battery, and you're going to operate something. Close the switch. The battery's fully charged. Electrons flow out of the bottom of the cell, go around up through the LED, illuminating the LED, and then the electrons go back to the positive side of the cell. But the whole time this is happening, you're depleting the excess of electrons off of the outside shell and depleting the positive charges in the center rod. So eventually the battery will die and your LED will no longer be illuminated. If we add more circuits to this cell, basically we have 6 LEDs now, and we have 6 individual switches, and they are in parallel. So all 6 of these load circuits with their 6 individual switches are in parallel with the batteries. The battery's 1.5 volts. So if we turn on one LED, then we have 1.5 volts across one LED. But remember back to our storage system when it was a water tank supplying water to houses. The more houses that are drawing water, the faster you deplete the water level in the tank. If we add two batteries in series, voltage adds in series. So now we have two 1.5 volt cells, or a total of 3 volts. So we've got twice the voltage, which means the LEDs will illuminate twice as bright. Close the switch, current flows, and we closed all the switches, so they're all burning brighter than they did at 1.5 volts. But keep in mind, because we're drawing 6 times the current for 6 times the LEDs, the resistance is also increased, so we don't have 6 times the current. But we do have more current with two batteries in series. Two cells in series gives us 3 volts. If we put them in parallel, we still only have 1.5 volt, but we have, this would be, if I back up here a second, this is a higher water tower, higher voltage. This is the same height water tower as one battery, but because we've got two, that's like having a water tower that's twice as big around, but the water's still the same height over your house. So you didn't increase the height of the water column, just the total amount of water available in the reservoir to discharge down the downcomer to your house. So in this configuration, two batteries or two cells in series are going to give you twice the current, roughly twice the current, and the LEDs are going to burn twice as bright, but still no longer than they would have burned at half the brightness for one cell. With two cells, they're going to burn at the normal, they're going to illuminate at the normal level, but for twice as long because there's more capacity. Okay, that's enough for now, and we're going to stop in our basic introduction to electricity and magnetism. I hope you've gained a good insight, and as always, I really enjoy doing these presentations. They're not rehearsed, as you can probably tell by hemming and hawing and laughing at my mistakes, etc. I tried using a script. It takes hours and hours to produce a good script. Then what happens is you're reading the script and not necessarily thinking about what you're talking about, and you miss some good illustrations. So I lecture the same way in the classroom. I just throw up the slide, and whatever comes to my mind, that's what I talk about. Again, thank you for listening. Thank you for watching this training video. This was presented by the PLCprofessor.com and the PLC Professor YouTube channel. The PLC Professor website has a complete training package available for programmable logic controllers. This video was originally developed to bring people up to a level of understanding of electricity where they could transition into understanding relays and then a programmable logic controller. If you do decide to purchase the PDFs on www.plcprofessor.com, we always appreciate that you don't pass these on to your friends or give them away. I have priced them low enough where everybody can afford to spend the price for the 3 PDFs. I make all of the videos, 62 of them, free on YouTube on the PLC Professor channel. So the only support that I have for producing more videos is from the sale of those PDFs. Again, thank you.